First you go blind.
Everybody get logged in. Get logged in on your calculator, please.
Beautiful day for calculus.
Get logged in on your calculator, please. You can't log in on your calculator? Let me see if I can.
Killing it.
That's okay, because I just need a presenter.
Dude,
So.
it's a good day.
So long.
What?
All right, everybody logged in?
Don't forget to record. Are you recording already?
Ooh, Emily.
He's already recording.
Spell that.
He's recording?
Okay, get logged in here.
I was ready.
Oh, okay.
Jared, Casey, Emily.
Mine's not connecting.
But you want to pick up the center and then I'll log in?
I might just pick you up purpose.
Oh.
Let me see who's not logged in real quick. I'll pick him.
I know, I was logged in after you picked it.
Will you tell me? Yes. One of these days I'm picking you. Just on me. Jared,
Yeah. Oh, I'm the presenter?
you're the presenter.
Wow, I Normally I forget to sign up and do it.
All right. Let's get started here. So let's start with the worksheet. Now, were there any of those? There are some issues here with the calculator. We got to make sure that we get straightened out when you put these in. Now, first of all, when you type this into your F1, into your graph screen, you're only typing this part, right?
Yep. Right.
That is the function. So it's like you're doing the limit as x approaches 0 of some function f of x. Now, we're going to be talking today, and I don't know if you guys noticed, but the first three there all have a special look to them, do they not?
Sure do.
I mean, look at those first three. What do they all look like? The definition of the derivative, right? Now, that had no bearing on how you work them out, right? I mean, you just work out a limit problem the way you work out a limit problem. There's three ways we can talk about with some algebra, which when we first learned the definition of the derivative, that's what we did, okay? Like on this one, we could do a conjugate, right? We could work this one out using algebra. We could do radical plus one, top and bottom. Nice things would happen, and we could have come up with our answer to number one doing algebra. Now, we couldn't do this one with algebra, right? Because you can't distribute. There's no such thing as distributing sine to there. There is a rule for sine of 2 plus x that you could expand out, and maybe some nice things would happen. There's nothing we could do. Well, there probably is some algebra here, but not any algebra we're going to worry about doing. Actually, I think, and we would need more than that. I mean, like e to the 1 plus x. Couldn't I write that as that? E to the 1 plus x? Think about that just a second. Wouldn't that be true? Because what do you do when you multiply? You add the powers, right? So working that backwards, if you see power that is added, you could have written it like that. So we really could write this top as this, right? And then what could you do with that? Factor out e, right? And then you would have e to the x minus 1 all over x. But does that really do anything for you? I mean, as far as getting something to cancel or something like that, nothing really happens. So again, an algebra or a limit problem, square in the rectangle, right? Every square is a rectangle, but not every rectangle is square. Any derivative problem, like the first three there, they're limits, because that's the definition of derivative. But limit problems don't have to have anything to do with derivative, like number 4. Doesn't have anything to do with the derivative, right? So sometimes you get a limit that's a special limit, happens to be the f prime. So when we talk about number 2 here, this red thing, you could graph that in your calculator and look at the table, and you could get the value of this limit. But if we're going to think of it as a derivative, we would think of the f of x being something else. Instead of that being our function, we would say, well, as a derivative problem, what is the f of x here? As a derivative problem, what is the f of x?
2.
No, that's the a. sine of x, right? This is like the 2 plus h in here, right? This is like the 2 plus h. There'd be an h there, there'd be an h there, there'd be an h there, right? And take out the x's, put h's in, and this would be a derivative problem. See, that's part of the back side of the worksheet, actually, that we're going to be working on later. Okay, so this is actually the sine function, and what we're saying is this limit is the derivative at 2, right? Because of that 2 there. That's like the a. So, in one sense, we're graphing this on our calculator. So let's just do it. So Jared, go ahead and put this one in while I'm talking here. Go ahead and put this into your F1. Okay? And so on the one hand, we're just doing that limit, right? And we're treating this as a function, and we're putting it into our calculator under F1, and we're thinking of these as outputs, right? And our table is showing these outputs right here, the table we're going to look at in a second. And it's showing these outputs, okay? And we're seeing what these outputs are approaching as x is approaching 0. But those outputs also kind of have another meaning. Those outputs are slopes, because that's what this is, right? Is a slope. This is the slope of the sine function near 2, right? And so those outputs have a separate meaning. They're not just output numbers. They're actually slopes of the sine function near 2. Okay? So we've got to understand that kind of that connection. All right, so as we go and look at this, so Jared's got that up there, so let's hit Control T, and get our table in there. And we want to start our table at what? 0, because x is approaching 0, so we're going to go to Table Settings. We're going to put in 0. We're going to put in a small step there with a couple of zeros at least, maybe 3 even. It's okay, whatever. And then hit OK. And arrow up. Couple. And so we want to copy down that table. And we notice that on both sides, it seems to be approaching 3 decimal places where we want to go. We don't care that this is undefined, like a hole in the graph. That's okay. The cars are coming in here at this value of negative 0.416. So we come back to our worksheet here, and we're getting an answer here. And I know you can just type this whole thing on your calculator screen and get that, but 416. But that has 2 meanings, right? It has 2 meanings in this problem. It's the outputs of this guy here. It's the outputs of this function as the inputs get close to 0, but it's also the slopes of sine at 2, right? What's the derivative of the sine function? Cosine. So how about if Jared went on his calculator screen and typed cosine of 2? We better get that value right there, right? We better get that value. And go to the calc, just hit scratch pad. I don't know what will happen if you just hit scratch pad right now. Yeah, it just takes you to there. Do cosine of 2. And I'm guessing some of you tried that on that one. Maybe you typed that whole limit just on your calculator screen just for the heck of it. And it probably said cosine of 2, right? Anybody do that? Maybe try that. If you just typed in that limit problem number 2 as a limit, right, like I showed you yesterday, which I don't think is necessary for the understanding of what we're doing, hit Control Enter so we get a decimal. And there it is, right? There's that. All right, so you didn't have to think of that at all as you were doing these problems, but I think in the big picture, as we go towards our quiz, and just for things in general, I want you to understand that. Now, I said the first 3 had that special look to them. Do you see any others here that have that special look that look like they would be a derivative? Five is. Yeah, we actually had this one. This was number 35, I think, in our homework a couple days ago. It had cosine h minus 1 over h as h approaches 0. And so this is the cosine function, and it's the derivative at? No, that's the derivative. Derivative at what point? 0, right? Because this is cosine of 0 plus h in here, and then the minus cosine of 0, which of course is 1. So this is fits the definition of the derivative. And the others aren't. The others are just plain old limit terms. Okay, Katie, what was the one you and I were looking at? With those e negative 5 and weird things going on. Was that 10? I thought it was an earlier one up here too. 6, yeah, let's do 6. Jared, put number 6 in there. And I want to show you guys something on this. What'd you get for an answer on 6? Was that does not exist?
I put negative infinity. Just because I have no idea.
Is that the one that had the big number? What was the one that had the?
Yeah, it had really small numbers.
Oh, yeah. Oh, that was 5. Yeah, put in 5, Jared. Put in 5. Okay, on 6, yeah, 6 you would put does not exist. And you were getting numbers, depending on how many zeros you put in when you made .001 on your step, you were getting numbers like 3333, like big numbers like 33,000 or 3,000. When you see those, that's infinity, right? So what you have is an asymptote situation. So if you plug in a 0 here, you get 0 over 0, right? But there's no algebra, nothing you can do to it anyway. But you get 0 over 0. So what's happening though is you're getting asymptote situation. Now they might. There was one of them where they were both going negative. Was that the one? Was that number 6? They were both going negative. So what you have is a graph going down like this. Now the cars will not meet. So technically there's no limit. So it should be does not exist. Now later we're going to talk about infinity. And what I will say when we talk more about infinity is I'm going to say if you get a limit that does not exist, you have to tell me why. Well, there's really only one reason why the limit doesn't exist. The cars don't meet, right? Which means the best way is, and I think I might have said that in the directions, discuss the one-sided limits, okay? I'm not going to make that as big a deal on this quiz, okay? But if the limit doesn't exist, the first thing you'd ask is what's happening on the left and what's happening on the right. Something weird's got to be happening. That's the only way the cars don't meet, right? So in this case, negative infinity, negative infinity. Now, since both cars are going to negative infinity, some books would say it's okay to go ahead and say the answer to that is negative infinity, okay? But it still does not exist, because remember, the answer to a limit is a value, a number. Infinity is not a number, right? It's the number where the cars meet, okay? So if they both go to infinity or negative infinity, you could put that, but really you should put along with it, does not exist. Okay, Jared, you got that up there? Yeah. All right. So what Katie and I were talking about this morning on this situation is when you look here, now yours is set different, so I wonder if there's some different, go hit over, highlight your table, because Katie's didn't look like this, and I want to see why. Go to your menu right now. Go to table. Go up to actions. Well, go to document. Yeah, the doc, yeah, there you go. Go down to settings and status. Go to document settings. Huh. I wonder, is everybody's looking like Jared's? Yeah. That's what I was looking. Go ahead and escape out of that. How many people are getting theirs to look just like Jared's? How many people have a whole bunch of decimals? Huh. Okay, Jared, you're not presenter anymore.
What?
Sorry, you've been
Rig
recorded.
shit's me.
How
do I fix mine?
Well, actually, yours is okay. Oh, this person doesn't have that on. Okay. Well, who's got it on there with a bunch of decimals? Who's got this problem typed in?
I do.
Katie, you have yours?
Yeah,
I do, but then Nicole does.
Your what?
I have that. That's my screen.
Nicole does.
Yeah, that's my screen.
Oh, are we on number 5 right now?
Yes.
Yeah.
Oh, so that did happen. Oh, anyway. Yeah. Okay. So, well, okay, so Nicole, go to your table settings. Go to .001 there. Okay. Go to your table settings again. I want to make sure we cover this so that everybody, no matter what you're getting on your calculator, so put 0 there again at table start, and then put another 0 in there. Now hit OK. Huh, that window seemed to get bigger. That's not what I remember yours having, Katie, right? What does yours have right now? You on that? Yours have what we... That's your inspired.
Jerry got fired.
Just mad because my calculator's better than everyone else's.
So it's easy then.
Yeah, well, kind of, not.
Simple enough, no.
Hey, where's Clay?
I would be at the bottom.
Well, I don't think it's out.
I'm right there.
There he is.
Like right there.
All right, here we go. This is what Katie was seeing on her.
What?
Is anybody seeing that?
Yeah, that's what I
Okay.
Why you mad, huh?
Now, okay, so let's talk about this. So if you saw this, and you just put this down in your table, now what is the answer on 5? 0. That's going towards 0. But if you looked at this, to me, if you copied that on your table, I wouldn't be very excited about that. As far as if this was a quiz and you typed that in there. I mean, you know what I mean? Because to me, what you've written right here, that does not look like they're going towards 0. You see what I mean? I mean, 4.99, I know it's negative 9.99, negative 4.99, but how do we know it doesn't stop at negative 2? Or, you know what I mean? How do we know the car on the left's not at negative 2 and the one on the right's at positive 2? See what I mean? To me, that doesn't show 0. But now if you highlight this and put your cursor over it, and just leave your cursor over it, you see that there? It's a 10 to the negative 4 is what it is. See, but it doesn't show you that always in there. So you want to put your cursor on them, and so you can see this, and it's also down here, right? You can maybe see it down there. But what does that E negative 4 mean? Times 10 to the negative 4. So it's really negative 0.0004999, right? So that tells me it's really getting towards 0. So I would want you to either write 0.000499 or the 10 to the negative 4th part of it. Make sure that's in there. So don't just copy that because you're not seeing the whole thing. Does that make sense? Okay. Now, if it's 0.004, then yeah, clearly that's getting towards 0. Now, Katie, we had another one. At number 10, it was really kind of strange numbers. That one was also 0, wasn't it? On 10. 9. 9 is also 0. Now, that one, when we investigated those cells, it jumped from 10 to the negative 5th to 10 to the negative 4th and back to 10 to the negative 5th, which was weird. And some of that's just the accuracy to calculate. If you're seeing 10 to the negative 4th, 10 to the negative 5th, that's going towards 0, right? I mean, because that's 0.000 something. So that clearly that's getting really small towards 0. Okay? All right, so that was the thing I wanted to make sure we talked about. And then if you look at, so I guess, Clay, you're the presenter now. So if we look at, I also want to look at number 8. So put number 8 up there, Clay, for me. Now, to get the absolute value bars, you have to go into that next to the 9 to get that. There is a vertical bar button. I think I showed you a while back, but we haven't really needed it. There is a vertical bar button if you look above the equal sign, but that does not work for absolute value. You can't do vertical bar, then something, and then that vertical bar. That doesn't work. So you've got to go into, well, at least one place. There's probably some other places, but you got to go into this thing next to the 9. I think you can type ABS also as a function. You go ABS this that one. Yeah.
For the calculator, how'd you get it so that it was like times e to the negative?
Well, that's just it. I don't know where that setting is. What were you getting? Just 0.00.
Yeah, 0.0000.
That's better. I mean, if you got that, then that's easy, right? Because then that's 0.000, and you can tell that's going towards 0. So that's less confusing. So if yours is doing that, that's good, right? I don't think you want it to say, 4.999 e to the negative 4, because then you got to make sure you understand what that means. You know what I'm saying? So it has to do with the cell widths, and I'm not quite sure why some is doing that and some aren't, because I'm not sure where that setting is. So it doesn't matter if yours isn't doing that. That's actually probably a good thing. All right, so now we look at this, and here we notice right here. Notice how it doesn't say undefined, which is okay, right? I mean, understand what's happening. When it says undefined there, we either have like a vertical asymptote or we have a hole. But we don't care when it comes to a limit, right? If it's vertical asymptote, of course, it's undefined. But all we really care about are these numbers as they come in towards 0. We really don't care what's there. Now, if it happens to match with what's coming in, then that's great, right? That's great. That means if we go back to this original problem, is this x approaches 0, right? Remember, the first thing you do on a limit problem, if you're doing it without a calculator, the first thing you do is plug a 0 in if it's x approaches 0. If it's x approaches 3, you plug a 3 in. So in this problem, we put a 0 in. 0 minus 2 is negative 2. Bars make it positive 2. Square root of 2 is 1.414. There's your answer, right? So it doesn't surprise us that we're getting, an answer there, but we really don't care. It's what these numbers are approaching. And it happens to be the same thing, so that's like a bonus, So we got 1.414. Okay? And that happened on that one that was E. Didn't one of them come out 2.718? Number 7? 3 and 7 both? 3 and 7 both came up to that, right? And on one of them, wasn't there one of them where it wasn't undefined? On 7? Did you get undefined right at 0 on number 7?
Yeah.
Oh, it did? Okay. All right. I couldn't remember that.
The only one was 8.
The only one was this one,
Yeah.
where you didn't have undefined right at that spot. Okay. Well, anyway, that's all I really wanted to talk to you about on that. Now, while we got the calculators out, let's talk about what could happen for the quiz. So one option would be where I just give you this. I just give you a limit problem, right? And we, like this, and I say justify it using a table, right, on your calculator. So this is what you would do, just like you just did that, okay? So that could be something that you would do. Now, another problem I could give you might involve the definition of the derivative. So if I ask you, so I'll just give you a second here to try to set this up on your own. So if I said, okay, let's do the derivative. Let's do one that we could actually, no, let's don't. Let's do this. Let's say I wanted you to do the derivative of, I'm going to tell you that f is tangent x, and I want you to find f prime of 3. And my directions would be, using the definition of the derivative, right, set up a limit that will find f prime of 3. And then use your calculator table to answer to solve the problem. Okay? Go. Use the definition of the derivative to set up a limit and use your calculator table to find. Okay? And you can talk with each other if you want.
And it says x approaches 0.
My directions would be, use the definition of the derivative to set up a limit and use your calculator table to find the answer. Awesome.
About 9 people. So,
Yeah, it's kind of it's actually
Oh, okay. I got you. Yeah. Okay.
All right. Can I put the limit up here?
I thought you had to
Ready?
solve this and prove it by
Right?
Yep.
Right? We have to be able to set up that limit because one of the things we did at the beginning of chapter 2 is work these out the long way, right? If I ask for, if I just gave you a function and said find f prime of 3 using the definition, right? Your first step is this. Your first step set this up. Now, when we first were doing them, if this was no calculator, now you'd have some algebra to do here, right? Maybe a conjugate, maybe a common denominator, maybe a factor and cancel, right? But here I've picked one where none of those things work, right? And so that's why this is a good candidate to do with a calculator, right? On the table, or maybe with a graph, because the algebra techniques just aren't going to cut it for this one, right? So you got to be able to just set it up, because you're going to have to do that in a variety of problems. So now, yeah.
So it's not as h approaches 3, it's h approaches 0.
Right, great question. It's not h approaches 3, it's h approaches 0. Why is it h approaches 0?
That's because math guys are trying to find the slope of 3.
Yeah, the definition of the derivative, Casey, right here, the definition of derivative is always h approaches 0, because what's the h in this?
Gotcha.
What's the h?
It's 0.
No, but what's the h in the definition of derivative? It's the distance, right? This is a slope between 2 points, x and x plus h. H is a distance between them. We want the 2 points to become 1, right? And that's the h. So h has to go to 0. So you're right. In the definition of derivative, and I'm glad you said that though, because I get that every year. Every year, people on a problem like this, when they go to set up that derivative, will, if it's f prime of 3 or f prime of 2, they'll put that down here. No, the 2 or the 3 is up here. And again, I think it's, go to this. If you're doing f prime of 3, that means there's a 3 right there for that x. Well, that x is the same as that x is the same as that x. Right? So a 3 goes there, then means a 3's got to go there, and a 3's got to go there. Now, what we haven't talked about here yet is, okay, when you're going to do this in your calculator, this is what you put in your calculator, right? This part. Do you put an h in? No, because you're going to put it into your graph screen, and what letter do you always put when you go into your graph screen? X, right? So now you're actually going to put x here, just like you did on today's assignment, right? So you're going to type that in, but you're going to put x here, and instead of h approaches 0, it's x approaches 0, right? Because that's what you use on your graph screen. Okay, all right. So, Jared, or who's up? Clay? You got that in? Okay. So the first thing would be to set that up. The second thing would be to put that in here. And it looks like the 3 decimal places, I feel pretty comfortable that that's going to be 1.020, right? Yep. Positive 1.020. Now, if we know something about the tangent graph, right? The tangent graph comes up like so, and here, and where's this asymptote? Pi over 2. And then this one comes up right here. Now, what's this value right there? That's pi, which is 3.14. So at 3, we should be right in here somewhere, right? So it's starting to kind of level off, right? It's pretty steep here, but it's kind of leveling off. So we're talking about a tangent about like that. And what did you have? 1.020. We'd want to go 3 decimal places, and that looks pretty good. Okay, that looks pretty good. Okay, so I feel pretty good about that. Now you have your calculator, right? I mean, so if this was on the quiz, so you could put it, what am I looking for? Oh, I could go to my calculator screen, just put that limit in if I just wanted to double check, whatever. But the key thing that I'm quizzing you on there is that you can set up this limit. You understand how to set up this limit, and then you understand that you'll put that part into your calculator to check the table, right? Much like we've done on this worksheet for ohms. Okay, a lot of different representations of the derivative or just limits and what's going on, and should have no problem with all those variations if you really understand what's happening. It's not about memorizing, right? You got to understand the concept of what's going on. All right, so that takes care of what I wanted to review for the worksheet, and then if we go back to our notes from yesterday for the derivative, or for the, for the quiz, right? We got all these things I was just talking about when it comes to limits. We worked on it yesterday in the homework quite a bit. right? When you do the graphs, it's really easy to do a limit on a graph because all you care about is where the car is going, where the cars meet, right? If they don't meet, it doesn't exist. So when you look at a graph, limits are probably their easiest. The algebra would be like yesterday's worksheet, you know, that common denominator stuff, the conjugate, the factoring, substitution. These things over here, I think it's important to go through. When you do substitute in a limit problem, you might just get a number out, so that's great, that's your answer. Most of the time you'll get 0 over 0, which basically means keep going. Keep going, do some of this algebra and something nice may cancel and then you'll get an answer. Or you may get a number over 0, another number but 0 over 0, and when you get that you just say does not exist because you've got some sort of vertical asymptote or something happening. So just say does not exist. Okay? And then, of course, we got the thing with the table, like we were just talking about. So if you got a limit problem and you're getting to use your calculator and it says do it with the table, you type that thing in and you set up your table and you can see where the cars are meeting, what's happening. Okay, that's it. I mean, that's it with limits, right? That's the kind of the whole story there. So let's, and then that does kind of carry back to this a little bit when we're working at, so now that we've talked all about that in 2.3, the stuff from 2.1 is pretty simple now, right? I mean, the stuff in 2.1, we just, basically the problem we just did would be like a 2.1 problem. Here's a function, I want the derivative at 3, do it using the definition. So you set up your limit. The only difference is the one we just did, we did with our calculator. You'll probably do somewhere you have some algebra to do that, right? You have some algebra to do and you'll do that. All right, so you'll have some problems then also where you get to use these shortcuts, and that goes into the chart kind of questions, and we had number 21 in our homework, so let's talk about that. Okay? So somebody want to read me the function that we had on number 21?
G of W equals 7 W to the 9. Take away 18 W to the 7 plus 63.
Plus 63.
Yeah.
So this is crazy. This is a 9th power. I mean, so this could literally have 8 humps, right? And it could have 9 different places it can cross the x-axis, and local maxes and mins and stuff like that. Could be all kinds of crazy stuff going on. All right, this is a no calculator. They also show you we don't always have to have f as our function and w or x as our input, right? We got w here. All right, so we want to find where g is what? Increasing?
Yeah.
Where g is decreasing, where there's a local max, and a local min. That's what we're interested in, right? So where do we look for those things? Where g prime is 0. So g prime would be
63
and this would be no calculator, so you're going to have to do 18 times 7 without a calculator, sorry. Okay? And the 63 disappears. Now that's a good thing because this derivative of 63, of course, is 0, any constant. And so now we get something that's nicely factorable, right? 63 w to the 6th, leaving w squared minus 2. So that would be when w is 0. Don't forget plus or minus. You have to remember that when you're solving, it's got to be plus or minus. When you square, because basically you're saying w squared minus 2 equals 0, so w squared equals 2. Whenever you square root both sides of an equation, you've got to have the plus and the minus. So now we've got, those are 3 stationary points. So we go down here and we make ourselves a g prime number line, and we put those 2, or excuse me, 3 things on there. Okay? Now, those are the places where g prime is 0. But what we really care about is what? When it's positive or negative. So if those are the 3 places it's 0, in between those places is where it has to be positive or negative. So we want to know some numbers in between. So what's square root of 2? 1.4?
Yeah.
So maybe negative 2. In here would be negative 1. and here would be 1, and here would be 2, right? So you got to pick some numbers that would be in between those. And they can be other numbers, but those are simple. We don't have a calculator, so let's pick something simple to plug in. Do not put, this is a little tiny thing but I think is helpful. I always put the tick marks on my number line at my stationary points. Do not put tick marks in here for these numbers. Because you do, and then it really gets messy. Right? We want to see that there's 1, 2, 3, 4 intervals here of between. Okay? So I sometimes see that, and it really gives people difficulty when you do that. All right, we're going to put -2, we're going to put it up here into G prime. Now, I could put it into here, but that's going to be not a lot of fun to do. It'd be a lot easier to put it into this version. And all I care about if it's positive or negative. So, -2, well, geez, what about W to the 6th? Isn't that always going to be positive?
Yeah.
Isn't that always going to be positive? Right? Because it's a 6 power. So I don't care what I plug in, this is going to be positive, so I'm just going to ignore it. It's really whatever this comes out to be. So that makes it a lot easier to plug into. I'm having positive times positive will be positive, or positive times negative will be negative. So I don't even care about that part over there anymore. So I'm just going to plug into this. So -2 squared is 4, 4 minus 2 is 2, that's positive. Put a -1 in, squared is 1, 1 minus 2 is negative. Put a 1 in, 1 squared is 1, 1 minus 2 is negative. Put a 2 in, 4 minus 2 is positive, positive. So what's going on at 0? Flat spot. I got a flat spot at 0 because that tells me right there that the G graph is going down and then keeps going down. But I do know it levels off because remember, these points are where G prime is 0. These 3 points are stationary points. It's got a flat. Local max, local min, or flat spot. I got all 3 in this problem, right? So where's G increasing? Well, it'd be -infinity to -√2, and from √2 to infinity. Decreasing in between -√2 and 2. Or excuse me, √2. Local max where? -√2. G prime. Now, again, you're probably going to have to justify on that one. So what I say yesterday, G prime is changing from positive to negative, so therefore G is changing from increasing to decreasing. That's why it's a local max. But you got to have that G prime G connection there, okay, in your explanation. And then local min would be the same thing. Local min here, because G prime changes negative to positive, so therefore G changes from decreasing to increasing. So all that chart stuff we learned and talked about in the last chapter with graphs, we can show like this with equations. Okay? All right. So that, be prepared to do that. That when I talk about in those notes, and I said for 2.4 be able to do chart stuff with equations, this is what we're talking about. Problem just like that. You're going to do another one for your homework tomorrow so you can practice. Okay, we just did the definition with our calculator. Let's do, okay, let's do, bite your tongue. Let's do this right here. F of x, we should practice. Well, I tell you what, never mind. Never mind. We'll practice that on Monday. We'll practice that on Monday. All right. Oh, yeah, in the book. I'm sorry, I forgot about 3 through 12. Let's talk about those real quick. 3 through 12, section 2.4. Okay, oh shoot, I hope I have a picture of this. Dang it. Okay, page 120, 120.
Oh.
Page 120. Okay, I do not have a picture of this one. Sorry. So they show you the little f graph, right? They show you the little f graph. So what is the slope of big F at 4? So what are you looking for? The y value on that graph, right? So if they're asking in this problem, they give you the little f graph, and remember, this is what you're looking at here. This is the order if it goes in derivatives, right? So if they give you the little f graph, that's the same as the derivative of the big F graph, right? That's what we talked about yesterday. So if they want the slope of big F at 4, that's like asking for big F prime of 4, right? Well, big F prime of 4 is the same as asking for little f of 4. Well, that's the little f graph, so you go to 4, and it's got a 5, so there you go. Where is big F increasing? Where little f is positive, which is all the time on this one, isn't it?
Yep.
0 to 10. Okay, where does big F have points of inflection? Big F, if we were looking at the chart here, and I think it's good for us not to have the chart right in front of us right now, big F would have points of inflection when it changes concavity. What's little f do then? Local max or min. It increases or decreases, or vice versa. It switches, increasing, decreasing, local max or min. So that would happen at about 1.5 or whatever. They gave you that number, I guess. 1.14 and at 8.19. So at the local max or min. So it's all that stuff we've had before. Big F's concave down when little f is decreasing. So from 1.14 down to 8.19, right? Okay, hopefully this is real easy. Big F double prime, well that would be here. Big F double prime would be like doing the slope of little f, right? That would be little f prime. So little f prime, they give you the f graph, little f graph, so you would draw in your tangent line there at 9. It'd actually be going up a little bit, right? So what'd you get? Negative. Oh, at 5, I'm sorry, I thought it was at 9. So negative 1.5, negative 2, somewhere in there, something like that. Okay, good enough. Why does F double prime, this was a little trickier, why does F double prime have a minimum at 4.67? Well, F double prime having a minimum would be like F prime having a minimum. F prime is the slopes of that graph you're looking at. So when the slopes are a minimum, meaning either they're the least positive or the most negative, right? Well, that would be at the inflection point where it's going down, because that's where it'd be going down the most, the steepest. So the slopes would be the most negative there at the inflection point, which is 4.67. Find an equation for line L. Now, they told you in the directions that line L was the tangent at x equals 0. They told you big F of 0 was 10, right? So to write the equation of tangent line, you need the slope of big F at 0. Well, what's big F? So that'd be big F prime. Well, what's another name for big F prime? Little f. So what they're really asking for is little f of 0. Well, that's 7. So now we got our slope. So we got y equals 7, x minus 0, plus 10. So we got our point on big F, and we got our slope on big F. All right, very good. And number 10, does L lie above the curve at 1? Does the L is the tangent line on big F. We don't know what big F looks like, but when does a tangent line above the curve? When it's concave down. When a graph is concave down, the tangent line is going to be above the curve. So this question really is, when is big F concave down at 1? Take your chart, big F's concave down when little f is decreasing. Big F is concave down when little f, its derivative, is decreasing. So at 1, is little f decreasing? Little f is increasing at 1. Little f is increasing. Let's pull that chart up here. Okay, here's big F, here's little f. Big F is concave down when little f is decreasing. Okay, and a tangent line's above the curve when the curve is concave down. So you had to put some things together. Is it possible that f of 5 equals 5? I wish I had this graph. Let's draw it. Okay, so we got this thing here. It goes up, comes down like this. Okay, is it possible that big F of 5 is 5? Now they told us big F of 0 was 10, right? Is it possible that big F of 5 is 5? Why not?
So it's increasing.
Since little f is always positive, big F is always increasing. So if you start a big F graph at 0, 10, if I draw a big F graph here at 0, 10, and it's always increasing, there's no way it could go down here to 5. Okay, no way. Could f of 5 be 15? Well, that means if you go over 5, you would go up 5, which means a slope of 1. So it means big F would have to have a slope of around 1. Well, the slope of big F is little f. Is little f 1? No, little f's up there at 7 and 8 and 6 and 5. So little f has way too big of values, which means big F has big slopes. So if you go over 5, you're going to go up way more than 5. There's no way you'll be at 15. You're going too fast, right? Speed limit law. Those are both speed limit law problems. Okay? To go over 5 and up 5, you have to have about a slope of 1. We can tell the slope because that's what the little f graph is. Okay, so those are all questions that were the same kind we asked back in the last chapter. The difference is in notation with big F. Only difference. Okay. We got a couple of new things to discuss today, and then we're pretty much done with new stuff, things that would be on the test, okay? Things that you would need, and we'll add that into our notes, and we'll go over that some more on Monday, but you get to practice. So, here's the first of them. We talked yesterday about how big F is an antiderivative. Antiderivate. Okay, that's not good. Antiderivative. Okay. The antiderivative. So, here's how I want to show this. So let's just do a couple lines here like so. So let's say that I had this is x to the third. Right? I told you that little f was x to the third. Now the easiest, of course, would be if I told you big F. If I told you big F, we could fill in all the rest, right? We could just go down and do the derivative. So if little f is x to the third, then f prime would be 3x squared. And then f double prime, 6x, right? Would be the derivative of that. Right? Power gets 1 less each time. So the question becomes, what would this be? 1/4 x to the 4th. Why is there got to be a 1/4 there?
Because
When you bring down the 4, yeah, whatever's here, we feel pretty good that it's going to be x to the 4th, right? I mean, we can tell by the pattern here, this has to be x to the 4th. Right. Problem is, when you bring the 4 down to do the derivative, you'll have a 4 in front. You'll have 4x cubed. And we don't want 4x cubed, we want 1x cubed. So there must have been something setting there that would cancel out that 4 when we bring it down. Well, that would be a 1/4. So, it's kind of a guess and check, isn't it? Now, we could actually make it a rule, though, and there is such a rule, but I will be honest with you, later in the year, much later actually, we're just going to barely touch on antiderivatives right now, okay? Because you're right, we haven't spent enough time with derivatives yet to really get comfortable with it. But we do want to talk about a few things, so we want to understand the idea of antiderivative. So it is just the derivative process in reverse. So since this has such a, I guess, rule that specifically laid out what to do. You multiply by the power, and you decrease the power by 1. So if you just do those 2 steps in reverse, you should have it, right? So think about it. decrease the power by 1. So let's do that in reverse and do opposite.
Divide the
So
power.
no, first would be increase the power by 1 and then divide by the new power. So the rule for now this is just the power rule, right? Because this wouldn't make any sense for sine or cosine if we're doing the antiderivative, right? But just for the power rule, that's all we're talking about. It would be add 1 to the power and divide by new power. And that would pretty much get it. So we would go x to the 4th and then divide by 4. Now I would agree with you. I'd rather you write down 1/4 x to the 4th. Okay. But then we're missing one other thing. Because couldn't it be 1/4 x to the 4th plus 7?
Yes.
Right? Wouldn't that work?
Yeah.
Well, here's how you check on antiderivatives. You just do the derivative, right? So you do the derivative, bring the 4 down in front. That would cancel that. X to the 3rd, and the derivative of this would be 7. Or 0, excuse me. And so what could this be, a 17?
Yeah.
Could be 170, right? There could be any constant there. So when we do an antiderivative, what we typically do is we just say plus c. Plus c. Some constant. When we do an antiderivative, it's kind of like when we drew the f prime, or we had the f prime graph and they want us to draw the f graph. We didn't know where to put it. There could be a whole variation of them that are vertical shifts of one another. That's what the plus c represents. Okay? So if I had 2x to the 3/2 here, what would be the derivative? I meant to put 3. So we bring the 3/2 down, the 2's are cancel, so we'd have 3x to the 1/2. The next derivative would be 3/2 negative 1/2. What would be big F? The x to the 5/2. And then what did we say? We said divide by the new power. So it'd be 2 divided by 5/2, which would be 4/5, right? You'd invert and multiply, so this would be 2 times 2/5, which would be 4/5. And if you check it, and this I would always do this, I'd always want you to check it, you'd bring the 5/2 down, so it'd be 4/5 times 5/2. 5's would cancel. 4 divided by 2 is 2. Checks out. Okay? So just raise the power up 1 and then divide by the new power. It's just the power rule in reverse for an antiderivative. The next quiz, not the one coming up, I guess that's the next quiz. The quiz after the next quiz, there will be some of this, so we'll practice it more. I don't think we're going to do any of that right now. Okay, there might be something about it in the homework, talk about antiderivatives a little bit on a few problems. So, you know, but I don't think we're going to put that on there. We'll just focus on this power rule, doing the derivative, right, going down the line like this. Okay, doing derivative. All right, so that's one thing. The second thing I want to talk about is on page 19, 16, something. No, it's farther back than that. I'm sorry. 108. I'll find it. Oh, here we go. 106. 106. One more. Now, I'm gonna have you write. Everybody should write this down. Okay.
Yes, sir.
You're not going to have to necessarily memorize it from the standpoint of you'll have to write it down for me, but you will have to use you'll have to know these things that are in here to use as reasons for some questions, which we'll get to here in a second. So a function is continuous. That's not how you spell it.
Continue.
Missing a U, aren't I?
Yeah.
Is that right?
Yeah.
Function is continuous at x equals a. So I'm going to do this a little different than where it talks about in the book. In the book, it talks about being discontinuous, right? It means not continuous. I'm going to talk about it in the positive, being continuous. Now, we've talked about continuous in the sense it just means nice and smooth, no breaks, no gaps, no holes, that kind of stuff. You have to lift your pencil. Some people think of that way, continuous. Okay? That's a little bit trickier to say, but when we're going to talk about breaks and holes and jumps and stuff like that, but I don't want you to use that terminology in your reasoning. I want you to use mathematical reasoning. Just like if a limit does not exist, and I ask you why on a quiz, I don't want you to say because the cars don't meet. Right? I want you to say that. I want you to say, well, because the limit from the left is 1 and the limit from the right is 2. That's why the limit does not exist. Right? So the whole thing about the cars not meeting is just for you to help visualize and understand, but you don't use that as a reason. Right? Because the diner burned down. Why is there a hole in the ground? The diner burned down. Yeah, that would be bad. We don't want to do that. So,
Oh, jeez.
all right, here we go. A function is continuous at a point A. Because a function can be continuous at a lot of points, just like we're talking about the limit, and then be discontinuous at some points, right? Now, if it's discontinuous at any point, then we say the function is not continuous, right? If we just talk about a function in general as continuous, we mean it's always continuous at every point. So what would make a function continuous at a point? Well, there's 3 things. Okay, first of all, f of a must be defined. Okay? Now what does that mean in a little more ordinary language? Well, it can't be undefined, but what's that mean? There has to be an output. The function has to have an output at point A. So there has to be, so there couldn't be a hole in the graph. So off to the side, what I'm going to do is show a couple of examples that would violate that. Like, for example, that would violate that situation. Or having like the tangent graph, right? You have like a pi halves, tangent is undefined. Okay, or we've seen some with a hole in the graph. So if the function's not defined there, then you've got a problem. You'd have to lift your pencil. It's just not continuous then. Okay. Number 2, the limit as x approaches a of f of x must exist. Now notice the terminology. When we talk about a function value, we talk about being defined or undefined. We talk about a limit, it exists or it does not exist. The limit must exist. Now, what would violate that? Well, right, piecewise kind of thing where the cars don't meet. Function's coming in, and then it takes off, and there's this break. Some people call that a break in the graph, like they did in the video, or a jump, or a gap, maybe, or something. And again, actually, we could use this same example with vertical asymptote. It kind of violates both of those. There's no function value at a vertical asymptote, and the limit doesn't exist. So clearly, at a vertical asymptote, the function is not continuous, right? Continuous, again, you wouldn't have to lift your pencil, that kind of thing, nice and connected all the way. All right? And then the third thing that has to happen, you would think that might hit all of them, but there's one last one, is the limit at A has to equal the output at A. The limit has to equal the output. Well, that would be the diner burning down and rebuilding at a new place. Right? Think about that. If you had a graph that did that, is number 1 satisfied? Is the function defined there? Does it have an output? Sure. Right there. Right? Is f of a defined? Yeah, it's got an output. Does the limit exist? Sure, the cars meet right there. So the first two are okay on that one. But it's clearly discontinuous, right? This is not a continuous situation, nice and smooth and connected. So this is clearly a discontinuous situation. So not only does the function have to have an output, and the limit must exist, the cars must meet, but the cars have to meet at the same place of where the output is. The limit has to equal the output. So if you've got all three of those things happening, then the function is continuous, right? So what I may ask you, and where you'll have to have this kind of somewhat memorized, is give you a graph, kind of like we had in the homework that had all those different breaks in it, right? And I might say, where is this function discontinuous? So I'll just pull that up again. So if I ask you, so here was a homework problem we had. So if I ask you, where is this function discontinuous? You'd say at x equals -3, -1, 1, 2, and 4. Those would all be places of something kind of weird going on that makes it discontinuous. Then I might ask, why is the function discontinuous at 1? And I want you to state one of those three. Why is the function discontinuous at 1? It's the third one, isn't it? No.
That's the second one.
I'm sorry, it's not the third one. It's the second one. The limit does not exist. The limit does not exist. Now you could say, well, it's the third one, the limit doesn't equal the output. Here's the output, and the limit does not exist, but it doesn't make, you know what I mean? Equals is something you do with two numbers, right? So it's really the second one is what you'd want to put there. The limit does not exist. There's a break there, but you could say break, but you also have to say the limit does not exist. That's what we're doing. So it violated number 2.
If you put the third one, it's wrong then?
That would probably be wrong on that one. That's why I drew those little pictures off to the side, right? Which one violates the third one? -3,
2, and 4.
2. Probably wouldn't give you one here because technically we talked about the limit because you can't see their side, but you're right. I probably wouldn't try to throw a curve on you on the end one, but -3 for sure and 2 for sure. The limit exists. It has an output, right? And actually none of these violate number 1, I don't think, do they? There's outputs everywhere. So if I covered up this dot, then at -3, that would violate.
It's still there.
Okay, so if I cover up that dot, then that would not violate number 1. All right. Or would violate number 1, excuse me, because there would be no output. All right, so that's what it takes for a function to be continuous. And with that, I don't think I have any more to do except let you work. So, I was going to help you on one. I know, I'm sorry.
I'm fine.
But I was going to help you on one that is like your homework.
So we should write it down, is what you're saying?
No, I don't think you need to write it down. Actually, there's 2 of them. What I've done is I pulled up an old sample test. I pulled up an old AP review test, which when we get after Christmas and start getting close to midterm, we'll start doing these practice test problems to help us get ready. Here's one of them right here. Now, again, I wouldn't worry about writing this down. But it always throws us off because we look at this and we want to do something with it. But actually what we should do is recognize what? It's the definition of the derivative right over there. So what we want to do, and this is what you're going to be doing on your worksheet today, we want to identify what function that is doing the derivative of and at what point. So what point is it at? They say right there 3. They could have put the 3 in there for the x, but they just wrote it up there. That's fine. Now what function is it? The x plus h is stuck in there where the x used to be, right? So this is absolute value of x. So what is the derivative of that at 3? Now you might say, oh, geez, I don't even know the rule for absolute value. Well, you don't need the rule. You need to know what the graph looks like. It's a v. At 3, what's the slope? 1. So that's all you would do for that problem. You would have to recognize that it's the definition of the derivative. The function is absolute value of x. They want the slope at 3, and then know what the absolute value, and those are always 1 or -1 on the v graph, right? So there would be your answer right there. Okay? Alright, so that's a little bit like what you're going to have on your homework today. You're going to have some of these limits. You're going to have, you have to identify what function it is, and so forth. Alright, one other one here I wanted to look at is this one. Okay, this gets to that idea, this idea of continuous. Okay, so what we have here is a piecewise kind of situation. It's a parabola, so that's always continuous. We have a sine graph, that's always continuous. This is a no calculator. Both of those were no calculator, by the way. If this function is going to be continuous, what does b have to equal? Well, what's going to make a piecewise function not be continuous?
If it's not, it's.
If they don't meet, and where will there be a problem with these meeting? When x is 5, right?
Yeah.
The problem will be when the parabola comes in at 5, does the sine graph take off from up here, or does it take off from the same spot? So in other words, really what this question is asking, or you tell me, how would I answer that? What would I do? I don't, yeah, you could draw graphs, but I think that's probably hard because you don't know what b is, right? Just plug in a 5, it's that easy. What you care about, that at 5, they both have the same y value. That's what you care about. If they both have the same y value, the one's going to stop and the other's going to take off from the same place. You won't have to lift your pencil. It'll be nice and continuous, and that's what the question's asking. If there's a break, then you got a problem. So you simply plug a 5 in for x, so you get 25 plus 5b, and you'd want that to be equal to 5 sine 5 pi hat. Now, on the AP test, they do a really good job of quizzing you on multiple things within the same problem. So right here, they're going to check to see if you know your sine values, aren't they? So 5 pi halves, what would that be? All the way around, that'd be 4 pi halves, and one more. So that'd be 1. So 5 times 1 is 5. So 25 plus 5b. 5b equals negative 20. B equals, so if b is a negative 4, these two will have the same y value when x is 5, making it a continuous function, and there's your answer. Okay? I think you have something similar to that in your homework today. Okay? All right, with a piecewise, and they ask where it's continuous. So, for today, it is on your assignment sheet, so if you want to look at that, get that out here real quick. You've got the back side of that worksheet, and it's called derivative limits. So if you look at it, they all look like the definition of the derivative. So you just identify what function it is, at what a point, and then I'm not even sure what else it says. It says f prime of a for some function f and some input a, identify f of x and a, which we've been doing here, and then use your calculator to estimate the value. So in that case, I don't even care about putting down the table, don't worry about that, okay? But just do it with the table, just for practice. So do it with the table, and then write down what they're approaching. Write down what they're approaching, okay? So you got that. Then in 2.3, yep, section 2.3, I think it says that on the assignment sheet, doesn't it?
Yeah.
2.3, you've got 61 and 63 through 67. Again, those are some problems about limits. I think that's where the last problem we just did with the continuous, I think that's in that section, okay, about functions being continuous and so forth. That's the limit section, so you have a little bit with limits in there. And then 2.4, number 20, remember we did 19 yesterday, that's the chart stuff. We did 19, you did 21, now you do 20. So again, just to get a little more practice with that. And then 31 through 34. And I think that has something to do with, that's talking about antiderivatives. So we were talking about antiderivatives a little bit there. And then 52 and 54. Now 52 is probably the toughest one there. So I'll understand if you have some difficulty there. Don't kill yourself racking your brain on that one. But 54 you should definitely be able to do. 54 is a lot like number 20. So 54 you should be able to do. 52, that's a tricky one. So take that as a challenge. Right? If you like a challenge, try to get it figured out. Yeah. Now understand, after Thanksgiving, if you go to the restroom, it's one at a time, and you have to put your phone in the nice big thing that we are going to have on our door. It's going to be exciting.